Okay. Well, for people who are joining us on the live stream, this is another episode in our continuing design of chemistry functionality for Wolfram Language. So without further ado, let's get started. Okay, molecule and graph functions. Okay. So the issue is, what is the issue here? Is to make specifically a chemical graph that is different from an ordinary graph? Really? You guys there?
Jason?
Sorry, I thought I was unmuted. So graph has lots of named constructors like complete graph or Peterson graph, and this would be a molecule graph that would produce a graph object.
Sounds good to me. And it's an ordinary graph object. In other words, things like double bonds are represented how?
Either as multi-edges or as properties on the edges. I don't know which would be better. Or they could be weights.
Okay.
The graph in the Wolfram language is very versatile, and you can have properties at the whole level.
Is Roger here? Did Roger join us here?
I'm here. Yes.
What do you think we should do with respect to double bonds and graphs?
I think you should have an option that specifics says what.
I think we need, at least at this stage, I think we need to be able to play with both.
Okay.
And Michael is probably right. But
yeah, that option should be the right. A double bond function or something. How do we specify? So double bonds, in the case of a molecule, instead of a two-way rule for an edge, right? You used to have a double bond there instead. Is that right? You have a symbolic double bond thing.
Right.
Okay. So really what we want is probably an edge conversion function or something, or a bond convert. I mean, one way to do it would be to say, to have a bond conversion.
I mean, the same applies to the nodes. You might want to preserve some of the nodes in some properties as weights.
Okay. But those are node. I mean, right? But that's something like which atom is this? Which type of atom is this?
Right. So something. So like when you go from the atom node to the vertex of a graph, you might want to preserve some things.
You might want to put the atomic mass as the weight, or you might want to just have it as a property name.
Or you might want to label it with the NaC.
Yeah, I think if this is a function, then all of these things can be accommodated, which is great, but I think we need to work through sort of, is this a useful mapping?
Fine, but we could have some named mappings here. So in other words, if we have a bond conversion function, what would be, it would be atom conversion function or what?
Right. And so it would take an actual function, or it would take a name?
I think it would take various kinds of curated names that do commonly useful things. But I think in general, it could take a function that operates on the canonical atom specifier and converts it. I mean, there's a fully decorated form of both an atom and a bond, isn't there?
Right. So a bond could just be bond list 1, 2 string single, or equivalently single bond 1, 2.
Well, whatever gets fed to the bond conversion function better have been canonicalized. We better decide what the canonical form is, otherwise people will have to write all kinds of crazy stuff there. Right, we better decide what is the, I mean, doesn't molecule canonicalize to some definite form?
Right. So the way I have it now, you can say single bond, double bond, aromatic bond, just for convenience. But then the canonicalized form, it's bond, comma, aromatic, bond, comma, single.
What do you mean bond, comma? What do you mean?
Bond list 1, 2, and then string.
Like bond like this?
Yes.
And then single like that.
Right.
Okay. Yeah. Okay. Fine. Well, then the bond conversion function, how else can you decorate the bond?
That's really the only property that we have.
Okay, so what about an atom? How do you specify an atom?
So the head atom, follow then the single arguments and association.
Okay.
Atomic number goes to 3. It's a bad example. Formal charge goes to 2.
6, whatever. Okay, so that you have something like this. So then, in principle, so we have to figure out how these functions. I mean, we could generally have bond conversion function, atom conversion function could be useful for other things as well. For example, for various kinds of exporting, I would imagine, maybe.
Probably not. I think handling the MIME types for the different formats would be an easier way to go. There aren't that many different formats anyway.
I see. Okay, fine. Right.
Also about these conversion functions, would they be a lot like the graph vertex label and edge label functions in the way they would be perhaps used or specified?
I don't really know because, I mean, yeah, I mean, another question, hydrogens are the only things that get, omitted. There's nothing else that you sort of omit because you don't feel like including it.
Right.
But it's not like, okay.
So hydrogens make up half of the vertices, but give you almost no new information. So they're often omitted.
Mm-hmm. Okay. Well, so I can't tell you exactly. Do you want to discuss these any further, or does this give a reasonable direction for what to do?
Right. I think that's a reasonable direction. We can come up with names like order to weight or bond order to property, something like that. But I can have a few different options for those things for the next meeting.
Okay. Okay.
So at the last meeting, it was suggested that adjacency matrix would just simply take a molecule and work on it. But given the different conversion options, it doesn't seem unreasonable to have to convert it to a graph before feeding it to these functions.
Well, so long as adjacency matrix can give a meaningful message. I mean, in other words, is there a canonical ordering of atom? I mean, in other words, which is atom number 1, 2, 3, 4, 5? Is that obvious?
No, I mean, it's only obvious in the expression that you had. They're listed in that order. You can also see them on a molecule plot or something. But no, I mean, we have a canonicalization, or we can have a canonical form of the molecule, but we don't reorder atoms to be in the canonical form.
What I'm asking is, to make a meaningful adjacency matrix, it matters what order the atoms are in, right?
Absolutely.
Okay, so given a molecule, given a particular representation of a molecule, is it obvious what the ordering is?
Yes, from a particular expression that you're given, the ordering is obvious. What's not obvious there is whether to include hydrogens or not. And I don't think that you'd want to give a new option to these functions, whether to include hydrogens or not.
No.
The important thing, though, is if you ask for the adjacency matrix, then ask for the atom list that they're consistent.
Yes.
Look, my criterion will be, if we can make adjacency matrix just work, we might as well, but I think it would also be perfectly acceptable to generate a custom error message that says, given that there's a molecule inside that you have to, and you're asking for the adjacency matrix, which you might reasonably expect would work, that it says you have to convert to a graph first. But we just don't want to leave it with the adjacency matrix of a molecule just producing garbage.
Right. Okay. Yeah.
Find shortest tour. Why would one care about that?
Let's that one I don't know in particular, but
why not? What's the shortest path to really come from one atom to another, especially for
the tour is to come back to yourself, right? So the shortest tour might matter for people who are looking at molecular circuits or electron paths.
Okay.
In a molecule.
Okay, atom list, bond list. I agree. Don't have a problem with that. I mean, it's a little unfortunate, our whole atom Q. Yeah. I mean, it is conceivable that we should slowly deprecate atom Q and replace it with some other name, because that's the only place where we use the word atom to mean something that isn't physical atoms. Oh gosh, it's from version 1. How is it updated in 2003? I mean, I could imagine leaf Q, although we might just be setting ourselves up for another unhappiness in a few years. It's a little weird, atom list, because, you know, that could mean something for an expression. It's like level, comma, -1, the leaves.
Right, but the alternative then is vertex list. Just having vertex list.
You didn't understand my point. My point would be to create a new thing that does the functionality of atom Q and slowly, slowly, slowly deprecate the atom Q function. Do you understand?
Mm-hmm.
Yeah.
Michael, do you have any opinions about that?
I think it's a very important function. Also, of course, it confuses people a lot, kind of they see something and can't get inside.
Yeah, but I mean, to say that it's an atom, it's really a question of whether it's a leaf. I don't know. I mean, let's put out.
Not really. The real question is, can you operate with part on it? This is the one that matters to people.
Yeah, right. Can you split the atom?
I mean, I've always wished that it was called normal Q instead of atom Q, but atom Q is what it is called.
Normal Q wouldn't be the right name.
No, normal Q, no.
False. Would be the reverse of this.
Right.
Splittable Q.
What's that?
Splittable Q.
Indivisible Q.
Yeah.
I was just going to say indivisible Q.
I don't think indivisible is right. It's what can you go inside? I'm reminded of the first common notion of Euclid. A point is that which has no part. That's what we're dealing with here.
I mean, it does in some sense have parts.
Yeah,
right. We can split the integers and the reals.
Yes, but not by, I mean, what it really is.
Not by part.
Right.
It's really a special function for part.
Yes. I mean, it's sort of subparts Q. Does it have subparts? Part accessible, partable. I mean, yeah, right. The truth is, in code, when people say atom Q in a piece of code, if it was more descriptive, it would actually help. Because for people who don't know the kind of history of you know, atoms in Lisp or God knows what else, it's not very helpful to see atom Q. You have to always explain it. Whereas if we had a name which explained it, we would be better off.
Well, you picked first and rest instead of car and cutter.
Yeah, but that's, and isn't that good, Roger?
It is good. I'm saying
yes, good. I like first and rest much better.
Right. So the question is,
I do not get that reference.
What's that?
I don't get the reference.
It's a Lisp.
Okay.
In Lisp, they call car and cutter.
Yeah, as a result of machine instructions on a what, an IBM 704 or something?
Yeah, 604 maybe.
I mean, our language is full of historical, not Wolfram language, but English is full of historical crud. And okay, in any case, I think it's a serious possibility that we should try and come up with a better name for atom Q. And I think it should be something about parts. Part.
The partition comes to mind, partition Q, but that is too close to the partition.
Absolutely not. There's a partitions Q function, which is one of those rare functions that ends with a Q but isn't a question.
Ah, okay.
Part accessible. I mean, look, this is probably the most descriptive of the names, part accessible queue. Let's bring this up. We have an LCC meeting that follows immediately this one. Maybe, let's see who's PMing in that meeting.
Maybe not today, because already the last time the subject at hand was delayed.
Okay.
There are a couple other people there for it.
Okay, fine. Okay, well, can we get it on the LCC agenda then for a subsequent?
I can forward it.
And also maybe send it to to the design mailing list. And
yeah.
Maybe here I'll send you these not very good names.
Yeah.
I actually like the idea of renaming it, because every time I've shown AtomQ to people, they say, "What is that?" Which is kind of not the answer you want. And you know, when we have an atom list and it has to do with molecules, nobody is going to ask, "What is that?" By the way, somebody is heavy breathing. Okay, all right. Isomorphism functions, chemistry aware, isomorphic molecule Q. What is the graph isomorphism thing? Is it graph?
Isomorphic graph Q.
Okay. Okay.
So the idea here is that with a molecule, they're not isomorphic if the bonds don't match, if the charges, if the atom type doesn't match up.
Sure. Okay. It doesn't seem wrong to me. I mean, okay, so find molecule isomorphism. Is there a find graph isomorphism?
Yes. And it returns a list of rules
that map the vertices.
Yeah.
Okay. And what would you return here?
The same, a map.
How do you apply that list? I mean, in other words, in the case of a graph, how do you even apply that isomorphism list in the case of a graph, Roger?
What do you mean by applying?
Well, I mean, if I wanted to take that first graph there and, you know, apply this isomorphism to it to get the second graph, how would I do that, given that's that first graph structure?
Look in the application. I think you can. You're just remapping the vertex names. Oh.
It's a big mess. Wow. What, I don't know what the heck this is showing.
Well, look in the scope then.
I mean, what would you want?
But you're just remapping the vertices.
You're just reordering the vertices.
Yes. I understand what you're doing, but I'm asking you structurally, how do you take it? I mean, I can't just say /dot and then replace those numbers, because I do bonkers things that way.
Right. You would have to take the vertex list and take its part. You could take the vertex list and the edge list and do a replace.
So the answer is there isn't a very good way. I mean, in other words, this is the analog of some kind of replace part.
But there is such a thing. Hold on.
For graphs.
Yes.
So what
vertex replace or some such. Hold on.
Okay, but so it isn't even referenced in find graph isomorphism. Okay, so but that's my question is how do you use the find? I mean, in other words, what would you do? So you look at the molecule isomorphism, you say, oh, that's wonderful. Yes, these things, I mean, it's sort of a proof that there is an isomorphism between those molecules, but then so what?
Right, to me, the isomorphic molecule Q is the more important of the two functions. If you want the isomorphism map.
Why would you want it? Tell me one reason you want it, other than to be convinced that it's true that there's an isomorphism.
It's important if you're trying to determine the symmetry of the molecule. It helps construct the permutation group, for example.
Okay, so explain that to me. So that permutation group is very directly like this is a permutation, right? The isomorphism is a permutation.
Yes.
How does it relate to, quotes, the permutation group of the molecule?
If you have all of the permutations, you just have to add the identity to it, and then you've got the permutation group. The permutation group is used in a number of applications of isomer counting and things like that. Possibly entropy calculations.
Okay, but so for those things, would you be taking the molecule and then effectively applying a permutation to its atoms and then expecting to get back another molecule, or what's the deal?
In my experience, we haven't done that, but we have used a permutation group to count isomers and different pathways of interconverting labeled isomers.
So one area where I've used the isomorphism map itself is, so when I was getting SD files from PubChem, they would have a 2D and a 3D for each molecule to show the diagram and the 3D structure, but they would sometimes have the atoms in a different order, and I still wanted to get the 3D coordinates from PubChem, so I had to use that map in the manner that's not so super convenient, but.
Well, okay, so but really what you want is, conform one molecule to another molecule.
Right, like an atom map between.
Right, but in particular, and I would even argue that would be true for graphs also. In other words,
there is a vertex replace, Stephen, but that is, I'm going to fix that. There should be a reference to it.
Yeah, and probably in properties and relations here. So vertex replace does what we would hope it would do.
Yes.
Okay. My one question, though, Stephen, is once you take this permutation and you apply it from one structure to another, what do you get in the end? You get something that's for all intents and purposes identical. All the properties you would compute from it would be the same. About the only thing that might be different would be the atom labels. I'm not sure, though.
Well, the ordering would be
they might have different embeddings.
So the coordinates wouldn't move, just the labels and the bonds and so on would move, or something like that. But this is what you would have to work out.
Okay, isomorphic molecule Q, for example, if there was something labeled there, it's going to ignore the label for purposes of molecule isomorphism, correct?
Yes. Correct.
It's not totally obvious it should do that. In other words, you could have a thing which says lock this particular thing, maybe. Maybe I'm wrong. Am I wrong?
So you mean specifying which properties are considered for isomorphic, like don't consider formal charge, do consider formal charge?
Yes, that would be one issue. But I mean, I'm just trying to understand. It could be that for some exogenous reason, the one little iron atom. No, of course, it was one iron atom. Which never mind. I mean, then you know where it is, so to speak. Let's say there are two iron atoms. And for some exogenous reason, that this iron atom can't be exchanged. Does that make any sense? Or am I just being confusing? Maybe it doesn't make any sense. But then the question is, so you're saying isomorphism of molecules throws away annotations, but doesn't throw away physical properties, like this is such and such an isotope and so on.
I believe that's the way most people would expect it to behave, or to be used. I've only seen it used as a test, as it were. I've never actually seen the permutation being used and applied on one structure or another.
Yeah, I mean, all I'm saying is I think finding the permutation is basically a proof.
Yeah, the only application I can think of is if you did it on substructures and you wanted to align two three-dimensional structures on a subset of the atoms, and you would want to find the mapping from one molecule to another automatically, and then bring the two structures into the same 3D space with those atoms superimposed.
But as Jason was saying, he needed to use it for almost that application of 2D, 3D correspondence.
Yes.
And so there could be a function renumber atoms, because vertex replace can do a lot more. Vertex replace can take a vertex and replace it with a do vertex that wasn't there. Whereas here we're just talking about reordering. If you would apply an isomorphism to a molecule, you would just be reordering the atoms. So you could just have reorder atoms or renumber atoms.
Is it renumber or reorder? The atoms have, the atoms have numbers, yes?
Yes, they're usually referred to by their index in their position in the list.
But they could also be named, couldn't they?
Right. You could also.
Yes.
You could also. Yeah.
So what do you do if it's a molecule with named atoms? What does find molecule isomorphism? Then does it end up in its list of rules having things like, X goes to Y type thing, as opposed to 3 goes to 17?
I would think it would have to be the 3 goes to 17 to be completely unambiguous. And those labels, X and Y, would just be carried along.
But wait a minute.
To the new positions.
The labels, but is it obvious? I don't even understand. Does every atom have a positional label? Or do some atoms potentially have labels which are just explicit labels as opposed to positional labels?
No, every atom has a positional label, and some atoms also were given a name when you created them, and they can be referred to by the name.
I see. Okay, fine. But the name is just decoration and will be carried along, but it's not part of the so I mean the name, I don't quite understand. If I've got some 3 carbon atoms and one of them has a name, 2 of them have names, do those become then non-identical carbons that can't be interchanged in an isomorphism calculation?
No, but we could make it an option to include names, but I would assume not.
Okay. But then after you've done the find isomorphism,
then you moved a named atom from one position to another.
Okay, so the issue here is, do we need a function that says
to return the map?
Well, the map is the find molecule isomorphism. The question is, right, that's returning the map. The question is what applies the map? And that's your renumber.
Reorder sounds better.
Yeah, it sounds better to me too. And which is vertex replace in the case of graphs? That is the analog of vertex replace, which would eat find graph isomorphism output.
Yes.
Okay. Humph. All right. Well, I mean, for the time being, we could say molecule, I don't know what the molecule reorder or something, molecule, I don't know whether, I mean, we could call it molecule reorder, something like that.
Okay, I can make that up.
We have something called a canonical graph.
What does that mean?
It's just a normal form of it. So if you, it's isomorphic to the original graph, and it just uses canonical labeling. Mm-hmm. Always 1, 2, 3, and so on.
And two graphs are isomorphic only if their canonical graphs are same Q, right? Or is that?
Yes.
Okay. But so, are you proposing that there be a canonical molecule as well?
I don't know. I mean, it's kind of useful when you want to compare a graph to a large collection of them.
Yeah.
And that's the sort of a big use case for, canonical graph.
Can we overload the graph functions here for molecules?
Right. The functions that end in the word graph, do we want to overload?
Not really, no.
Right. But some functions I would like to use, like connected components specifically. Connected components returns a list of graphs.
I don't see any problem with using that on molecules.
Okay. And then
a submolecule? I don't know what to do with a submolecule.
Right. I would want molecule extract to do what subgraph does, it seems.
What is molecule? I mean, what else would molecule extract do? If it has hanging, flapping bonds, does this have hanging? I mean, I don't even know how you represent a hanging bond.
Right. So all of the molecule modifying functions that I would propose that we would have, they would be smart and they would handle hydrogens. So if you had a 4-carbon chain that has 10 hydrogens on it, when you chop off 2 of them to extract them, then we're going to put a hydrogen in the right place, unless you give the option and say, there would be options of what to do with hydrogens and what to do with the dangling electrons. If you chop a bond in half, you could have one electron go to each half and you would end up with an unpaired electron. You could have both electrons go to the extracted part that you're taking, in which case you change the charge. Those would all be things that these modification functions can do.
Okay. Which modification? I mean, you've got molecule extract, but are there other ones?
Right. So
the subgraph one. Yeah, no, this is the subgraph one. Go ahead. Yeah, what?
So then the last item, the last section is about the molecule modifying. We would want to, so there would be tons of things we would want to do. Graph, you can add, replace, and delete edges, vertices, and whatnot.
My gosh, there's a whole.
So the thought, right? So the thought is, instead of having a single function for all of these, when to be honest, we don't know which are going to be the most useful for users, we have a single system level function that takes so if you expand the first one, atom add, the function is molecule modify or modify molecule. Takes a molecule, the second argument is a string, it tells you what you're doing, and then that from that second argument, the third argument makes sense.
It's okay. I mean, it's reminiscent of how we control a web browser or something, which is kind of weird, but yeah.
Because at the moment atom add or adding an atom isn't all that useful because you're just adding a disconnected atom, but we would still like to have the ability to do that.
Yes, well, I mean, if you're going to have this, I don't understand why that molecule. I mean, the thing that applies a permutation, that applies the isomorphism permutation, should surely be another modify molecule thing.
Mm-hmm. Okay,
that's the only reason why it couldn't be.
Right.
Yeah, that would be a good place to put it. Modify molecule, renumber atoms or something like that, reorder atoms, and then the permutation.
Yes, I think it's fine for, that is a perfectly reasonable molecule modification thing. Now, this is all different because these things, hunt and peck and add and subtract single atoms and so on. But whereas the submolecule is doing something a little different. Is that a fair statement, or could you put the submolecule? Is the submolecule a very common operation?
Yes.
Right. So you've got this molecule that has it's got a sugar and it's got a furanose ring, and you want to take that and attach it to some other molecule. So the easiest thing would be you extract it, you end up with a molecule that you got back from the extraction, and you use that in your substructure replace on another molecule.
That's beautiful.
Yep. People often have fragment libraries, and then they can use them in different positions and generate virtual libraries of molecules for what they call in silico screening.
It's a shame we can't do the same kind of things with graphs. That is, extracting a subgraph and then gluing a subgraph back, or can we, Roger? What happens when we glue subgraphs? How do we do the renumbering when we glue subgraphs?
Well, subgraphs maintain where they came from.
Fine, but in the substructure replace, somebody has to renumber some nodes, or it could get, blown up.
I don't know. Don't they? The primary thing is what, right? It's like carbon or, Well,
I know that, but you have to label which node. It's representing a graph in the end. And the problem is that your substructure, let's say you have 10 atoms in the thing you're inserting into and 8 atoms in the substructure you're inserting. You can't, the numbering has to be realigned. The pointers have to be realigned.
Right.
And so I'm asking, how are these guys doing that? Pointer realignment and substructure replace. I'm
guessing, you got to sort of, the names, you have two things, right? And you have to refer to addresses in the one thing on one side and addresses on the other thing on the other side. Clearly.
Yes. Right, but your molecule here on the right-hand side doesn't have, that molecule, let's imagine you said 1, 2, 3, arrow that molecule. That molecule itself has 1, 2, 3s in it, right? So you're going to have to renumber the 1, 2, 3s in that molecule object because they're no longer going to be. Get what I'm saying?
Yep.
So what do you actually do?
Right. So as right now, I envision replace substructure. You're taking the substructure that is atoms 6, 7, and 8, and taking it out, and then putting in this whole new substructure that has its own bonds, and there's just one attachment.
I understand. That's all well and good, but nevertheless, in the specification of the graph, in the substructure in the molecule you are inserting, right, that graph will have a numbering in it. 1, 2, 3, 4, 5, for example. Okay, those numbers have to be changed at insertion time.
Yes.
Right. So I'm asking. I mean, something has to change. So the assumption is the receiving molecule doesn't have its numbers changed, but the molecule being inserted does have its numbers changed. Is that right?
I think
yes, that's what we used to do in other modeling systems that I've worked on.
Right. Michael's made the point you would, if there was an atom 9, 10, 11, 12 in the original molecule, you would expect those to change their numbers as well. If you're
they fall down, so to speak.
Also, if you're losing hydrogens because you took away the heavy atom they were attached to.
All right. So you're saying that you realign. I mean, it's very reminiscent of compacting garbage collectors or some such other weird thing. You're realigning all the pointers, starting at the beginning. So atom number 1, if it so happened to not be involved in the extraction,
it's kind of like a linker.
Yes, it's a linker, right? Okay, so let's talk about what the analog of that is for graphs, Roger.
So we don't really have. You can't substitute a whole graph into a graph.
So arguably, you should be able to.
Well, you can do the disjoint union and then add in an edge, right?
Yes, you can. You can, but you know, there's a whole thing that Stephen is after, really. But that there's another, you know, a deeper. If you want to do many of these and you want to do it efficiently, you have to build different kinds of structures to do repeated replacements.
No, I understand that, but it would be good to start off by just being able to have a way of doing replacements at all.
Yeah, actually, I think this argues for the molecule object being part accessible Q false.
And part of what you want there, Steve, you know, actually, what I had in mind, if we were to continue on this too, which is very important to basically have a notion of hierarchical graphs, where you can actually do abstraction there. Then you need to have a clearer model, so not just a flat replacement, so to speak, even if that's also interesting. But then, you know, then you have to. There's a large set of cases to inventory of use cases. I mean, of inventorying, because there's different models of how one might do that. So, for instance, UML, which is based on state charts, has one very successful model of how to do hierarchical graphs. And there are more, but one has to go through them all, you know, to get sort of a sense of what's the meat.
So when we look into that, the proteins and other larger biomolecule systems would benefit from that, from coarse graining the functional groups, coarse graining the amino acids to make to have a
So do you have any idea, Roger, what I mean, instead of having a vertex, you'll have a subgraph somewhere, but the vertex...
Right, but you need to... The trick is, what is the outside interface to that group?
No, I know.
The interior. And that's the trick, you know. It's
in the universe modeling business, we were calling those hairs.
Okay. Is the universe modeling business big?
No, it has a very small number of the total head count is very modest.
But yeah, I think that those are, you know, but they're pretty interesting, you know, to to do. But in the end, I think that there's more than one answer.
The problem with hairs, I'll tell you, the issue with hairs is, or tentacles, whatever you call them, right? Dangling bonds, whatever you call them, right? Is that whereas for a graph vertex, one generally thinks that and this is something again that got messed up with this. A graph vertex has 4 edges coming into it, right? You think of those edges as being, indistinguishable, right?
Okay.
But in fact, you might want them, but by the time you have a whole subgraph sitting underneath there, those edges clearly aren't indistinguishable.
Yeah. Actually, my point was that we need something, something that would be the different modes of doing this. But one thing that we've encountered before is sort of the notion of ports, so in system modeling is that, say, all these come in here, that tells me the outside connections, and then you have to specify the wiring one level down where they'll
Sure,
go.
and the same thing for the neural net, for net graph.
Right.
Mm-hmm.
And so the system modeler business is exactly like that,
Right. So, okay, but so we can call them ports, hairs, tentacles, whatever. But the basic bottom line is they might have ordering or they might have names.
Right.
Yeah, well, that is something we need to figure out how that's going to work. Okay.
And then you want to define renderings for those, layout schemes. And typically, there's another generation of then optimization layout schemes, because then things have size in a different way. And so then you get very closer to, much closer to VLSI layout kinds of things, where you actually need to take into account size for the layouts. Mm-hmm. This is useful to do anyway in some ways, but I'm just saying it's a different level. It's a different.
Yeah, I understand. Do we have an active project thinking about this stuff?
No, we're fully committed to geometry, so there's just not a lot of going into that.
Yep. A lot of times when this is done programmatically in chemistry, the fragment libraries are set up in such a way that they're really only being joined with 2 ports being chained together, or just a single port and being attached to some substructure that has N ports. So the embedding, as it were, and the size aspects are minimal to be dealt with. In other cases where it can be much hairier, as it were, it's done with a graphical editor, and the chemist has full control of placing things and moving things around, and then size, is just dealt with naturally by the user and the graphical interface that they're working with. And then it's cleaned up with a geometry optimization under some reasonable energy model.
So that's very similar to the system model of how you connect wires together and so on.
Yeah.
Right. But System Modeler doesn't currently run, it's not fully autonomous layout algorithms. It's help you, but you as the modeler, can control everything.
Okay. All right, let's go back. Okay, so the question here is, we've got...
And in VLSI layout, the actual, that's how all of these EDA companies built their business, was basically solving the layout problem.
Right.
By the way, just for fun, Intel and others used to have layout girls. So you have a giant sheet of Mylar on the floor, and these are big sheets. And then you have layout girls that draw the layouts on these Mylar sheets in the 70s into the 80s.
Yeah, well, when I was doing the stuff for the NKS book, I had these graphs to detangle.
Yeah.
You remember? Do you remember this? I forget whether you we.
Yeah, I remember it.
Tried to find students to do it. There was this one young woman who was just exceptionally good at untangling graphs, and I looked her up many years later, and she has a company that makes custom knitting designs. So, go figure. It's really interesting actually, because she was spectacularly much better. We just gave people these tests, and she was spectacularly much better than anybody else at doing them, and completely bizarrely good at them. Like, I couldn't in any way see that the graph would untangle that way. Interesting. Anyway, but I think nowadays our graph layout algorithms are better than any human, much better than any human, and that's probably true. It's presumably true with VLSI as well. Yeah, and they're real. There are sort of performance objectives that you have there. There's certain speeds. The connectivity length determines the speed at which the circuit goes, for instance. So it's kind of, and also your use of real estate is kind of, so there are various things that you want to optimize in those kinds of layouts. They have something interesting that I wanted to introduce in future layouts for us, which is layers. So a modern VLSI circuit have, probably something like 15 layers. And when you build a circuit, you drill a hole effectively and get down to that layer. Because otherwise everything would be roads, like or sure. I mean, otherwise you can only get a planar graph. Right. And so what you're saying is that this is a way of doing layout where things are going to cross over, but you can imagine that there are a limited number of layers in which the crossover occurs. Because probably there's probably an easy theorem that you only need 2 or 3 layers to do any graph, maybe even just 2 layers. No, but you can sort of compute how many layers you need. In 3D, you can always do it. Sure. But yeah. It's a funny thing, and I remember ever since the late 1970s, people saying, the secret to the future of VLSI is 3D VLSI. Now it's happening, kind of. Is it? People have said it's happening ever since the 1970s. Yeah, but these, what are the memory guys? What are those memories that we have on the phones? Sims? No. The permanent memories that we use on the phones. That we also have solid state disks for now, SSDs. Those, they've started, both Samsung and Micron are now, and Intel are building 3D layouts for those. Oh, which are more than your 15 layers or whatever. They're actually. Yeah. Yeah. Interesting. Okay, we is that a spelling mistake or is that something that should be added to the spelling dictionary?
I think the latter. I Googled and accessor is used by other people, specifically in programming, but yeah.
Am I sending it in? I'll send it in. Okay. Okay, so what we're agreeing here is fine molecule isomorphism. We're reluctantly agreeing returns a permutation. And the question of how it's applied, for right now, we're thinking molecule modify would do that.
Would take reorder atoms as a string second argument.
And then, oh gosh, this is a mess. Connected molecule, because it's probably a connected graph queue.
Right. I specifically need that to check if whether I'm going to compute 3D coordinates. I want to know is it connected or not or something. So it's useful.
Right.
Yeah, and in fact, if you're doing a substructure replacement, you might forget to add, a couple, connect a couple of ports that you need to, as it were. And this would be a good check to make sure that you've, done all the bookkeeping you need to do.
So, just my ignorance here, but the molecule that's not connected, is that still a molecule?
By IUPAC nomenclature, no. The IUPAC nomenclature that would handle everything that we are calling a molecule is molecular entity, which I just think would be terribly confusing for us to use. But so our molecules can have a charge, whereas technically if it has a charge, it's not a molecule, it's an ion. And our molecule can have disconnected components.
Okay.
Because we don't have a reason to disallow them. So so spoke with Charles about this. Rather than having all of these different things, these properties available as sub-values on a molecule, we split it up. Some of the properties are going to be intrinsic, and some of those are going to be more geometric or.
Sorry, I don't understand. Why is it not? Why are they not all sub-values? Even if some of them have to be computed sub-values, and some of them are just structurally sub-values.
Let's see. So the point that they're hard to discover. So some of these sub-values, when you look at the documentation page for chemical data, it's huge because it has a couple hundred properties.
So what?
And so for some of these naturally grouped together, like the geometric properties, asking for the bond length of a particular.
So what? I mean, so we have autocomplete, and so we have other mechanisms for discovering. What is your solution to that? That is.
But what does it mean to group them? I don't understand. What do you mean?
There would be separate functions, like there would be geometric property, there would be molecule descriptor. And...
Nobody's ever going to remember what they are. Nobody's ever going to remember which one is which. Yeah, they'll never remember which one is which. It'll always be. You'll always have to look it up. Anyway, I have no idea what these PEOE VSA _VSA. What on earth is that?
Right, that's something surface area. When we come
clearly, num aliphatic rings isn't going to cut it as a name.
Right, I'm not saying that all of these should be heads, but I was saying that they should.
No, but not with those crazy names. I mean, they've got to be. Yeah. Anyway, so look, I don't understand why you want to break these up into. It doesn't seem sensible to me. Unless, I see. So here, certain properties are specific to particular atoms, and other properties are global to the molecule, right?
Correct.
It's really pretty much like entity property. Like normally we can just use entity of string property, but if we have something really complicated with enough qualifiers, we want to form a proper entity property that we apply in.
Fine. So why aren't we just calling these properties? Why aren't these just properties? I mean, couldn't we have, when we have a molecule which is in our database, couldn't these properties just actually work? If we say benzene, open bracket, benzene as an entity in our database, open bracket, monoisotopic molar mass should just work as a property for that. And it would also work as a sub-value to a custom created molecule.
Right. So I guess after the last meeting, I was feeling some resistance to just throwing all of these things into the two properties. And so I thought,
which properties?
So at the last, you had said possibly making formal charges a head. And then,
I don't know how important it is relative to all these other things.
Right. Let's see.
But the Hall-Kia alpha doesn't. I'm sure it's very important, but I don't know what it is.
It's a graph invariant.
I figured it was probably something like that.
Yep.
But there are many graph invariant. I mean,
there are the kappa 1, kappa 2, all of those there.
They're used in machine learning or regression analyses for various things. You need to pull up these big.
By the way, do we yet have an encoder for molecules? I guess we don't have a molecule, so we don't have the opportunity to have a machine learning.
I'm getting an intern this summer who knows more about machine learning than I do, and we're going to try and throw something together.
Okay. Okay. So let's look at this for a second. I mean, so look, I strongly think that we should try to support those, we should try to combine the properties from our built-in molecules and our custom created molecules, and we should have the same mechanism. Just like you can say, the benzene entity, if I say something like, benzene, molar mass or something, it'll just work. I don't see why that doesn't work on a custom molecule as well.
Right. I made a list of all the chemical data properties that can be computed just from the structure, and we could support all of them. Yeah.
Okay, great. Okay. And then the kappa ones of this world, I don't see why we shouldn't support those for benzene also.
Right.
I mean, it's just a question of, I mean, you know, if we can compute them from a custom molecule, then we just take whatever the structure of the molecule that we were given there and compute it from that. And if necessary, we can pre-compute a bunch of them.
I guess my fear is that in a list of a couple hundred properties, things can get lost.
Okay, that's a documentation problem.
Okay.
That's a separate, I mean, I think for these properties, we are planning to have separate pages for every single property. And that means we can have guide pages for properties and all kinds of lovely things like that.
But we still need some way to get them easily in the language.
What do you mean?
Programmatically.
Get what?
The list of these properties.
Okay, but fine. But I mean, if the properties are the same as the properties of the chemistry entity.
So they are subset, not the same.
Okay, that's again a separate problem we can solve some other way. We shouldn't be messing around. You know, the discovery problem. And by the way, why do we need to be able to do that? I mean, look,
it's not just a discovery problem. It's like if you want to do things programmatically, I feel like you should always have programmatic access to everything. You should never be forced to use a documentation page.
No, I agree. I agree. And I mean, we've got examples. My favorite example is the list of musical instruments, which I don't know whether we ended up, you know, my suggestion was to put some of those things in the data repository. Some of these rather arbitrary lists of things like that. Anyway, this is not a reason to have, look, we should have a single uniform interface for extracting properties of molecules, and it should be the molecule structure, sub-value, the property you're trying to extract, I think.
So even if that's the easiest way, the way that it's used most often, then we would need some kind of a head for it. So molecule value would be what I would propose. So say you want to look at get that property for 10 molecules. Molecule value can take a list of molecules and a single property. And then, so forget
that's reasonable. I mean, that's the analog of entity value.
Yeah, that's what I'm saying. It's really modeled 100% after entity value.
So forget about geometric property and molecule identifier. Yes. We can throw all those in.
Yes, I think so.
Okay. And then there was just one more topic on this that I wanted to touch before we left. The idea of caching 3D coordinates across kernel sessions. I don't have a prototype of how this would be done, but I think it would be interesting.
I don't see a problem with that. I mean, we've got other kinds of caches that are being kept in the local object store.
Okay. So I'll look at how those are done.
This would be something along the lines of persistent value.
Yes,
right, but persistent value stays in the user-defined place. This would be in a system spot or something, right?
Why in system? Wouldn't the molecule, if the user built the molecule, its coordinates or whatever they built about it should be in the the user store.
Yeah, we can't do it in a system level thing. That has too many.
Well, but if we are doing it automatically,
if they store it, we shouldn't store it.
So I'm talking about doing something automatically, so that when they enter a molecule, they quit the kernel and come back.
Yeah. For them, absolutely, it should be in their local object store.
Okay, the local object store. I will.
Yeah, and I think it should be configurable. That we could set it to be automatic. Some property, and it would automatically save everything.
The fact is, the function once just does this. It automatically caches, and there's a version of once that's coming. I think it's probably there in 11.3 that has a second argument, which is the persistence location, which will tell you whether it's session level persistence or whether it's, you can have cloud level persistence where it will show up in every one of your accounts and so on, every place where you use your Wolfram ID, etc.
So would it be something that they would have to use the head once?
No, not necessarily. I mean, we could probably have some caching mechanism built into these functions, but absolutely it cannot cache between users. It's got to be a single user. Well, a user could choose to cache it globally on their system, but we absolutely do not want any possibility of somebody, person A at pharma company X is studying this molecule and somehow their molecule winds up in a cache that's seen by, person B at pharma company Y. definitely very bad.
Right. I just meant that. Yeah. I didn't mean across users on a system.
Right. So, but that caching infrastructure, I mean, there's many different things that do that. So, for example, entities do that right now. That's what Nick has, this very elaborate entity caching system, which even does prefetching and so on.
That's what I was going to try and look at the prefetch to see how he's doing that.
I would ask Nick.
Okay.
Okay. All right, we've got more to discuss here, but this is all very lovely. And when do we expect, I mean, that the first version of all this stuff is actually going to be in the system?
I suppose that depends on when, how long we expect before the next release, not the one that's coming right up.
Yeah, I mean, look.
I think in a couple of months this can be.
All right, I think you should target that.
Yeah.
Okay. Okay. Great. All right. Sorry, I'm thinking about my next meeting here and noticing this this blog post that I wrote about sending kind of mementos of the civilization into space. This SpaceX launch that just happened had a pre-version of that put out by this crazy organization that I'm supposed to be an advisor to. So anyway, I'm getting distracted. We should wrap this meeting. Good. Okay. Sounds good. See you guys later.
Okay. Thank you.
Bye.
Bye.